The definite integral. Last video, we defined what Riemann sums were. However, we said that f had to be a non-negative function. Now let's extend the definition of Riemann sums to include any function that is defined on a closed interval a, b, so that your function could be positive, negative, or 0. We'll still let p be a partition of the interval a, b. Now we'll define the Riemann sum for this function to be exactly what we did before. It's a sum as k goes from 1 to n of your function evaluated at c sub k, where c is some point in the kth interval, times delta x sub k, which is the width of the kth interval. If we increase n in such a way that the partitions of p go to 0, then the width of every rectangle is going to go to 0. Here's a picture of what's happening with Riemann sums. Here's the graph of a function y equals f of x. It's both negative and positive. When f is negative, the Riemann sums are just approximating the area between the x-axis and your curve. And the area is going to be negative because your f of c sub k's are negative. So this will give you a negative area. And then up over here, this is just the regular approximation for the area under a curve. If the function f of x is continuous and non-negative on the interval, then the area under the curve over the interval AB is given by the limit as the norm of our partitions go to 0 of the Riemann sums. So this is different than what we did before for the area. In the last video, we talked about this sum here, but we hadn't defined what Riemann sums were. And instead of looking at the limit as our partitions had, the norm of our partitions head to 0, we had looked at the limit as n goes to infinity. So this is just another way of writing the same thing. And again, just remember, your c sub k's are points in your kth subinterval, and delta x sub k is the width of your kth subinterval. Alright, so now let's define the definite integral. Suppose we have a function f and it's defined on AB. Then the definite integral of f from a to b is written like this, right here, and that's going to be equal to the limit as the norm of the partitions go to 0 of our Riemann sums. The only thing we have to worry about is sometimes limits don't exist. If the limit doesn't exist, then the definite integral does not exist either. Alright, so let's talk about this notation here. This symbol here is called the integral sign. This dx right here is what identifies the variable of integration, and it should be written every single time you write an integral sign. They're a pair and they go together. And it's important that you know what your variable of integration is, because at some point you're going to start having more than one variable and you want to know which one am I integrating with respect to. This a right here is called the lower limit of integration. B is called the upper limit of integration. And this function here, f of x, is called the integrand. Alright, so let's do an example. Let's express this expression here, where p is a partition of the interval -3 to 3, as a definite integral. Alright, so here's our solution. Remember, we said the definite integral from a to b of f of x dx is equal to the limit of the norm of our partitions approaches 0 of our Riemann sums. So what we need to do is identify each piece. Well, here, going back and forth between here, limit norm of p goes to 0 is here. Here's our summation sign. Here's our delta x sub k is here. So my f of c sub k is everything that's left over. So that's this part right here. So we get that f of c sub k is equal to 4 times c sub k times 1 minus 3 times c sub k. And we know our interval. We said we were going to look at the interval -3 to 3. So that tells us to find f of x, I'm just going to replace each of these c sub k's with x. So I get f of x is equal to 4x times 1 minus 3x. And we get our answer that this limit right here is equal to my integral from a to b, so negative 3 to 3, of my function f of x dx. All right, so let's continue talking about areas under curves, Riemann sums, and definite integrals. So we've already seen that if I have a function f and it's continuous on negative, non-negative on the interval AB, then my area is given by this formula. So that means I could say my area under the curve on the interval AB is given by this definite integral. All right, so let's use this to do this example. It says graph the integrand and use areas to evaluate the integral from minus 5 to 5 of the square root of 25 minus x squared dx. All right, so first you have to look at the integrand, which is the square root of 25 minus x squared, and notice that that's of the form y equals r squared minus x squared, which is the upper semicircle of radius r centered at the origin. So here we're going to have, well, 25 here is my r squared, so that tells me that r is equal to 5. So I can go ahead now and graph my integrand here. It's the upper semicircle of radius 5. Now I need to evaluate this integral, and the only thing I know is that that integral represents the area under the curve from minus to 5. So since it's an upper semicircle, we can easily find that area. We know that the area of a circle of radius r is pi r squared, so that means the area of a semicircle is 1/2 pi r squared. Since r is equal to 5, we get that our integral from negative 5 to 5 of the square root of 25 minus x squared dx is equal to 1/2 pi times 5 squared, which gives us 25 pi over 2.